Hello.
Yes.
I'm going to describe precisely the problem we are solving, which is predicting the response rate of their events, and then I'm going to describe our method. I'm going to just give some description of how we do model fitting in a math-reduced framework, and finally some results of experiment. I won't talk about future work. I won't have time. Future work will be in the future. So here is a 6,000 feet overview of computational advertising. We have users visiting a page which is published by some advertiser. I'm going to refer to user page combination as an opportunity in this talk. And then you have a set of advertisers who want to grab the attention of the user and advertise their products on the page. So the advertisers participate in what is called an auction through ad networks, for example. So ad networks are commercial intermediaries that facilitate the process of matching advertising ads to opportunities. So for instance, Yahoo, Google, MSN, they are all ad networks. And recently, this has become even more sophisticated, and we have moved to what are called network of networks model. So we have ad exchanges where the participants themselves could be other small networks. Right? So there is a commercial intermediary, and the commercial intermediary selects from the set of ads the best ads to show for a particular opportunity, and that results in revenue and clicks and conversions and all that. So that's what computational advertising is. Now the next question is, how do we pick the best ads? So there are several components that are used to select the best ad. One important component is response rates. So when we show an ad to a user on a given page, we want to estimate what the click rates or conversion rates are. And that is generally done through some statistical model that continuously learns some data that is obtained through feedback. Then there are advertisers who specify their desire to advertise through what are called bids, right? So bids is again the amount of money you're willing to pay to win the auction. And the intermediary or the ad network takes the response rates and bids and uses some function of bid and rate and selects the argmax of the participating ads and shows them to the particular auction. Right? So this is what is done, and of course there is a lot of magic in that app which I have recommended. Right? Okay. So if you look at this function f, although the bid is known, well, that is also changing, but I'm not going to go into that. The response rate is generally not known. It's unknown, and it needs to be estimated, and that's where all the data mining methods come into the picture. So at the end of the day, the goal is to maximize revenue and advertiser ROI. If you think of the problem in a very abstract way, this is more like an explore-exploit problem rather than a pure prediction problem. You explore on rates that have been estimated from data that have been obtained so far, and you explore what is potentially good by taking risks. And this is quantified by various estimates. And generally, what happens is instead of ranking the ad by f, you kind of transform the f into some f star, which is now a function of bids, estimated response rates, and estimated variance. Right? So that's an example of how you could do that. So in this paper, I'm not going to talk about the explore-exploit problem. What I'm going to do is I'm going to focus on a method that helps you estimate rates of extremely rare events like click rates, conversion rates, through by exploiting a hierarchical organization that is often present in the data. Right? And what the hierarchies help you do, what the hierarchical organization helps you do, it helps you reduce the variance in your estimate, and it helps you converge to the best ad more fast compared to a scenario where you don't have the hierarchical system, right? So again, this is our data. Advertisers participating to different. So our data is obtained from the right media ad exchange, and we have advertisers participating to different revenue models. CPM is something where you pay by ad view. CPC is something where you pay some money if your ad gets clicked. CPA is again you pay if your ad results in a conversion, which is typically a sales on the advertiser landing page. So in order to, since there are different types of advertisers participating in the auction using different revenue models, the way we run the auction is as follows. We compute what is called the expected CPM. So for instance, if you have a click-based campaign, the expected CPM is going to be the click rate estimate times the amount of money you are willing to pay for click. If it's a conversion based estimate, it's going to be the conversion rate estimate times the amount of money you are willing to pay for conversion, and so on. So So one thing I want to point out here is it is not, in order to do this, you need absolute response rate estimate. It's not good enough to just do a ranking problem. You need absolute response rate estimate because you are normalizing across different pricing times. It's very different from sponsored search models. Okay, so again, conversion rates, and there are two types of conversion rate. One is called post-click. So you click on an ad and then you go and buy something. There is also something called post-view, where you buy something and the conversion gets attributed to the last page which you saw. And if the last page you saw had the ad, then you kind of get conversion, right? So there are two different kinds of conversion. And what I'm going to do is I'm going to show you an experimental result where we get output of three different rate models. Right? One is the model that estimates click rate, one is the model that estimates conversion per click, and the third one is the model that estimates conversion per page view. Okay, so here is our notation. An opportunity. So I'm going to ignore the user from the equation for simplicity, right? So an opportunity consists of a publisher ID I and X of T are the set of covariates which you may have attached to publisher. Similarly, an ad consists of ID J and X of A are the set of attributes which you can have attached to the ad J. Your responses consist of two different things. The number of successes you have when ad J is shown on opportunity I, and the number of times the ad was shown on opportunity I. And the goal is to estimate response rates within all these advertiser publisher cells in a very high dimensional continuous scale. So the set of publishers and the set of advertisements you have in the main system is extremely large. So this is an extremely high dimensional sparse contingency table estimation problem. The problem is challenging because the response rates are extremely low. So if you look at the set of all possible cells that we have data, a large fraction of them don't even have any successes. Right? So extremely high dimensional categorical. Imbalanced sample size among the cells where we don't see any clicks. The number of tries which you have in these cells have a huge variation. Right? Some cells have 5 tries, some cells have 5,000 tries. So it is imperative to perform some smoothing and do a small sample size correction to get reliable data estimates. And now the question is how to perform such corrections in a scalable way. There is of course one unique way. We all heard about the undecided theorem yesterday about shop formula. So I'm going to just show you just one way of explaining this. So what I'm going to show is the data which we have is aggregated hierarchically across both the publisher dimension and the advertiser dimension. So you can think of this as more like an OLAP style of aggregation. And what I'm going to do is we are going to describe methods whereby you can exploit correlations at different levels of aggregations in our data and refine estimated final things. So that's the basic idea. It's also referred to as shrinkage estimate statistics. So if you have a cell where there is enough data, you fall back on the maximum likelihood estimate, the number of successes by number of tries. If you don't have enough data, then you go back to your parent where you have a lot of data at coarse resolution and borrow strength from there. Another way to think about that would be the cell estimate is a weighted average of cells along the lineage path, and the weights are functions of sample size and correlation that you have in your data. Right? So this is the basic idea. So just for simplicity, let's assume every publisher ID comes with a path of length 2. So we know the publisher ID and we know the publisher type. For instance, every ad, let's say, comes with a path of length 4. So you know the ad ID, you know the campaign ID, you know the conversion ID, you know the advertiser ID. You can think of that as a collaborative filtering problem, for instance, right? You have a matrix of publisher by advertising, you have cells, you have data in the cells, and your goal is now to estimate the rates or the ratings in each of these cells. So this is like a collaborative filtering problem, except that there is additional structure in the data. The rows or the publishers have hierarchical aggregation that is available to you from domain knowledge. The advertising ads also have hierarchical aggregation which is available to you from domain knowledge. There is another very big difference of this application compared to collaborative filtering like Netflix. So in Netflix, what happens is Netflix is more like a matrix completion problem. You have a small set of ratings and you want to fill up the ratings of the other cells. Here that's not the case. If you have a cell where the number of tries is 1 million and you got 100 successes, you want your estimate to convert to the maximum likelihood estimated from that particular cell. So, but if you have a cell with only one success out of 5 tries, you don't believe in that estimate too much, right? So that's why it is different from the Netflix problem, although it looks similar to that. Okay. So here is our model. So So what we have to assume is the response rate for the kth record we have in our data is made up of two components. One is what we call the baseline probability. I'm going to describe what that means. Times the correction which is applied to the publisher advertiser cell, right? So the correction which is applied to the kth record for publisher advertiser cell Z is denoted by lambda zk. Now the baseline model which we get are based on some covariates, right? So for instance, you may know that the publisher is an entertainment publisher, and the user is interested in entertainment, and the ad is also an entertainment ad. And based on all the historical data you have, you may actually estimate a rough or an average click rate where an entertainment ad is shown as entertainment. So that is what the baseline probability does. And so now instead of working in success and tries, you work with what is called successes and expected number of successes. So what is the expected number of successes in a cell? You look at all the records that fall in that cell and you add up the baseline probability of each of the records in the cell. Right? And that's that's the expected number of success which you would see if your baseline probability if your baseline model is correct. Okay? So now at the end of the day, now what we have to do is we have to estimate lambda of z according to that particular model. Right? So we assume that the number of successes you see in a cell is a Poisson random variable centered around something which is a product of the expected number of successes from the baseline model times the correction. Right? So now all the complexity is in estimating the corrections. And again, the nice estimate of the correction would be just the ratio of successes by expected number of success, which as we just saw would not work because there is extreme data sparsity due to low response rate. So we need to do some smoothing. So again, I'm going to describe the smoothing model by using a very simple one-dimensional hierarchy with 3 nodes, right? So let's say there is a hierarchy like that. You have 3 different nodes. Now what is done is these are 2 different ways of actually doing the smoothing. Right? So in the first example, you assume that the response rates of the child nodes are centered towards the response rate of the parent. Right? So the parent actually has more data, so you expect to get more reliable response rates at the parent node. So what you do is you assume that if there isn't enough data in the child nodes, they are going to fall back on the response rates of the parent. Right? So that is the first model. You can equivalently write the same model in a different parameterization. So what you do is instead of having a lambda parameter for every cell, you actually attach a state parameter phi for every cell, and you reparameterize the lambda according to that form. So this model also does the same thing which the previous model does, and it does it by sharing a parameter, right? So the phi one here is actually shared among all the 2 child nodes, right? So the sharing of parameters makes sure you can exploit correlations in the hierarchy to get good estimated quantities. Both of them do the same thing. The first one is known as centered parameterization, the other one is called non-centered parameterization. And for our multiple hierarchy model, we are going to use the non-centered parameterization. So here is the idea. Let's say you have a publisher ad ID. The publisher comes with the path of length 2, the advertiser comes with the path of length 4. You attach a state variable to all the 8 cells, and you assume that the correction in that cell is a product of all the 8 corrections. That's the model. Now, of course, you need to constrain the parameters, otherwise this becomes the over-parameterized model. You have to overfit. So we constrain the model by putting what is called a spike and slab try. Okay. Right. So what the spike and slab try does is it assumes that the probability p, the correction is 1. Right. So you get no correction. Probability 1 minus p is some gamma distribution, which is the usual thing. And what this spike and slab try does is it gives you both good accurate model, at the same time it does variable selection for you as well. So there will be a lot of corrections where the posterior estimate is exactly equal to 1. Right? And again, in order to make it more precise, there is a theorem in the paper which you can look at, which tells you exactly when the correction is going to be exactly 1 and when it is going to be something bigger than that. Right? So model fitting, again we do model fitting. We could have done a subgradient method, but we found sequential 1 at a time update to be better for this particular application because it is more scalable, more amenable to map-reduced kind of computation. So what the sequential 1 at a time update does is it goes to every single node in your multi-dimensional space and updates the parameter in that cell conditional on the estimate of the other parameter. And you can easily show that the conditional mode of that particular cell is given by a closed form expression, which is this here. Right? So again, I'm not going through the detail, but this is all in the paper. You can read the paper and really get all the equations. But these are all closed form updates. So then you can do, you can use those closed form updates and you can do map-reduced computation. So since I don't have a lot of time, if you have multiple hierarchies, we estimate that by looking at the cross product of all k choose hierarchy. So let me show you some results. So we have three different data sets here: the click data, the post-click, post-conversion, and post-event. As I said, 90 billion records, half a billion records, 7 billion records. There are several features, two hierarchies. There are two different baselines I have also included here, which is so there is one model which does not use the hierarchy at all, right? Pure collaborative filtering style algorithm. There is other which actually collapses the cell. So it assumes that every ad has the same click rate as its advertiser, right? So these are just two baseline models. We also have a logistic regression model to compare against. I'm not going to go through the details, but think of this as the state of the art logistic regression which has been published in the literature. And let me show you some results. So these are box plots that show the lift in relative log likelihood compared to some baseline model for different methods. So let me explain you what the methods are. Let me just focus on the click data. The others are qualitatively similar. So coarser is the model where we actually assume the click rate for a particular ad is exactly equal to the advertiser. Right? It's a very coarse rate model. It is supposed to cut down the variance drastically, but it's going to incur a lot of bias. Fine grained model does not use the hierarchy at all, so it is going to actually incur a lot of variance. And then LM, LMH, these two are different variations of our model. One version encourages sparsity through a spike and slab trial, the other does not encourage sparsity through a spike and slab trial. The other three are different variations of logistic regression. So from the plot, what you can see is the new model is definitely doing a good job. In fact, both the parsimonious and the non-parsimonious ones give you almost the same predictive accuracy compared to the other model. Right? And now let me show you the effect that the spike and slab trial has as far as retaining the number of parameters is concerned. So for the click data, for instance, we had a model with 16 million features, and the spike and slab trial reduced it to 150 cases, which eliminated all other features. So it's a very parsimonious model, and we saw that even if you use a dense model without variable pruning, the predictive, you don't lose predictive accuracy. These are some rough computation times, so very scalable, 135 minutes for instance on 50 reducers. If you look at the logistic regression, it takes like 7 or 8 hours on 80 reducers, and these are again state-of-the-art logistic regression trainers which we use in our production system. So it's not something which we prototype for. Okay. So finally, to summarize, we presented a scalable map-reduced log-linear model to precisely estimate the response rates, and the key thing is we were able to incur precision by exploiting the correlation structure that are induced by the cross product of hierarchy structure we have in our data. And this is often the case in many data sets which we will analyze in this area. And the models are both accurate as well as parsimonious, and the parsimony is induced through a spike and slab trial. In fact, the parsimony comes in very handy when you are putting the system in production. Your cache size has to be very small, otherwise you cannot run different machines. So that's actually a very useful thing that we have. And we showed that this is significantly better than the state-of-the-art logistic regression method for the same problem that are widely used in computational